I hope others will join us. We told you have a cut, I think, at 12. So I hope they will join us. They will not be reading for the cut. So before we start, kindly, I want us just to observe just 1 minute silence in honor of one of our heroes in pharmacognosy, Professor Julius Mwangi, who was once our external examiner in pharmacognosy. We lost him and he's being buried today. Pharmacy has yet again lost one of its giants. It has been a difficult year, very, very difficult. Actually, the last 2 years have been very difficult for the pharmacy fraternity. We have lost quite a number of our colleagues, especially those who graduated in 1970, I think 1979. That's many years ago. But they are quite young because the majority of them either had just acquired their retirement age, or actually were before they hadn't even acquired the retirement age. So let us just, in honor of this hero who has really changed the pharmacy profession, shaped the pharmacy profession, let us just observe just 1 minute. And as he's being laid to rest today, each and every one of us, let us whisper a word to God to give this family comfort, especially the children, because he was only 70 years old, to give the family, the wife, the brother, the siblings comfort at this very difficult time. Thank you. Thank you for that. Let us now continue. Last time we were looking at the CNS stimulants, and we did classify them. We did look quite a number of them, number of the classes, and a majority of them were the phenylethylamine derivatives. And we were able to give examples. We were able to look at methylphenidate, phentermine, quite a number of them. We were able to look at the SAR, and we did, of course, mention the role of an alpha methyl group in terms of blocking metabolism, the role of an alpha N methylation, whereby we did see N methylation of course, we did mention just N methylation did increase activity, but if you did increase the size of the group, or the N atom, of course, the alkyl group, you had a decrease in activity. We explained steric hydrants, and of course, the small alkyl group increases lipid solubility. The molecule can be able to penetrate the BBB much better. We also talked about the stereochemistry of our molecule, and we did mention that the stereochemistry also has a positive influence on the activity of those drugs. Now we want to look at another category of drugs we call the hallucinogens, and even from the name, these drugs really do not have much therapeutic indication. But it's important for us to understand them because we will meet them out there. We might, of course, these are drugs that are abused by quite a number of people, and therefore it is good to know them, so that in case any patient comes in having abused these drugs, we do know what substances they are. So the hallucinogens, so we can start with the definition, and we can say a hallucinogen is a psychoactive substance that powerfully alters perception, mood, and other cognitive processes. So it doesn't alter them really positive. Of course, it will increase them. It will increase your perception. It will alter your mood. You might be very happy, laughing all the way, and also your cognitive processes. Hallucinogens are illegal substances in most locales or in most countries. They are illegal, and that's why we have seen they really do not have much use, although, as you are aware, we did have one presidential candidate who was talking about legalizing cannabis sativa. So they are illegal substances in most locales, and safety data is all but non-existent. Of course, the safety data becomes a little bit of a challenge because we would not do clinical trials of such compounds on anybody. And of course, when you talk about compounds that bring about CNS effects. Even when you use them on the mice, it's very difficult to know how the mice is feeling because it cannot express itself. But when you use other compounds, like some of the compounds that act in the periphery and you're doing some of the tests, at least you are able to, if it is having an effect on the heart rate, on the diuresis, you can be able to observe those effects, measure them, and be able to say these are the effects of the drugs. But drugs that work on the brain are really difficult to do their analysis or to do their toxicity testing, because we can only use animals, and of course we can also only watch how they behave, whether they are becoming excited. But of course there is no communication, so some of the many things will be, some of the many effects will be left out. Additionally, their use is uncontrolled, non-med their use in uncontrolled non-medical settings is extremely dangerous. Hallucinogens can also be defined as psychedelic, which means mind manifesting or expanding. It can also be called psychodysleptic, mind disturbing. They can also be called neurogen, producing dreams, ethiogen, producing religious experience, and indeed they have been used for such things. They can be called also psychotomimetic or psychosis mimicking. And when you look at this, even in their names, you can see there is really nothing positive about these drugs. Their classification first, we classify them according to their mode of action, and we do have the 5HT, specifically 2A. We do have the family of the 5HT. There is 1, 2, 3, up to 5. So we have 5HT 2A receptor agonists, and these are what we call also the classical hallucinogens. And under that, we have compounds that might differ in their structure. We have the egolines. Remember, we did mention egolines when we were looking at Parkinson's disease, the bromocriptines, egoline. We have the tryptamines, where we have the mushroom, and we have the psilocybin and psilocybin and psilocybin. We have the phenylethylamines. The phenylethylamines, again, this is not new. We have looked at phenylethylamines as, and of course, phenylpropylamines as stimulants. So we will try to see what is the difference in these phenylethylamines or in the phenylpropylamines. What's the difference in the structure, so that one molecule brings about stimulation and the other one is a hallucinogen, because there must be structural difference. Then we do have the serotonin releasing agents. These are agents that will release serotonin, and we have methylene dioxyphenyl ethylamines. So if you look at methylene dioxyphenyl ethylamines, again, that is a phenylethylamine derivative, but its mode of action is different. That is why we have put it in a different class. So the methylene dioxyphenyl ethylamine amines, and of course, we also do have methylene deoxymethamphetamine. So that's an example. So the methylene deoxyphenyl ethylamines, and an example is the methylene dioxymethamphetamine, or there is also amphetamine. So methamphetamine and amphetamine, both of them being examples of drugs that are serotonin releasing agents. Then you have the NMDA receptor antagonists. We have mentioned NMDA receptor antagonists when we were looking at the general anesthetics, when we mentioned ketamine. Remember, we did say NMDA receptor is a stimulatory receptor. So if you give an antagonist, then of course you will be reducing the activity of this receptor. So NMDA receptor antagonists, which we call the dissociates, and with the dissociates, because then NMDA represents N-methyl-D aspartate. The dissociates, where we have phenylcyclidine, or what is known as PCP. We have already mentioned ketamine. We have mentioned dextromethorphan when we were looking at the morphan derivatives. And then from that, so those are the NMDA. So that's another third category. The fourth category is K-opioid receptor agonists. And do remember, we did mention these are the kappa, also opioid receptor agonists, and we have salvinorin. We might not discuss that. I don't think I got any. Yeah, I think I have one or two statements about it. Then we have the CB1 agonists. CB1 agonists, and the CB1 agonist, we have the cannabinoids. The cannabinoids, and one of the most active, or what is found in cannabis sativa, is delta 9 tetrahydrocannabinol. So those are the classifications mainly, but as per their mode of action. So we'll try and now, of course, we look at the structural classification, where we will bring those which have similar structures together. But so so that's a classification, and we should be able to look at all those different compounds. So I think even when I look at them, I'll be looking like this class. I'll start with, let's say, the 5-HT2A, and then I'll look at the various classes in terms of their structure, so that is to maintain the mode of action classification. So let us start with the 5-HT2A receptor agonists, and these are the ones we are calling the classical hallucinogens. So under that, we are looking at the ergolines, where we look at LSD, we are looking at the tryptamines, we'll be able to look at psilocybin, and we're looking at the phenylethylamines, where we'll be able to mention mescaline. So we'll give the relevant examples. Again, these are not drugs, these are not compounds that are of any therapeutic indication. So I don't think we spend so much time, but we spend enough at least to understand them. So of course, we have said these drugs have an effect also on some of the neurotransmitters, and the neurotransmitters they're affecting most is serotonin, and that is a structure of serotonin. You can't see the difference between serotonin and dopamine, which we have studied. When you have reduced levels of dopamine, you have Parkinsonism. Even in serotonin, you can see the phenyl group. Of course, in dopamine, you also have the phenyl group, but you do not have the imidazole. You do not have the imidazole. But in serotonin, you have you have the indorine. You do have the indorine, which has the imidazole plus the phenyl. So, and of course, both of them, of course, dopamine is a catecholamine, serotonin is a phenyl hydroxyl derivative. So we are now looking at the influence. These are 5-HT2A receptor agonists, so they are increasing the activity of serotonin. So most hallucinogens increase levels of the neurotransmitter serotonin, which is 5-hydroxytryptamine. Classical hallucinogens are believed to act primarily on the 5-hydroxytryptamine or 2A receptor in the brain. These are the ones we call classical. And one of the, let us perhaps just go slowly. Me jumping the gun. The 5-HT2A receptor agonists, which we are also calling still the classical. 5-HT2A receptor is a G protein coupled receptor and a member of the 5-HT2 receptor family, but this is specifically 2A. It is known to play a physiological role in working memory, regulation of cognitive states, and associative learning. And also, it is believed to be involved in neuro disorders, including psychosis and schizophrenia. Common features of 5-HT2A receptor agonists. These are all the ones we have said. All of them. I think we have given 3. We have given mescaline. We have given LSD. We have given LSD. I think we have given mescaline. Which was the other one? We have given LSD. Ergolines, which was the LSD, and we have given the tryptamines. We have given the tryptamines, the phenylethylamines, and the ergolines. Those are the ones we are looking at the general, the common features of the 5-HT2A receptors. And we are saying most of the 5-HT2A receptor agonists are psychologically safe molecules that show no toxicity at active doses. So they're quite safe. In the millions of people who have used LSD, which is lysergic acid diethylamide, there is not one case known of death directly attributable to the toxicity of LSD. But now the effect it gives you, it changes, as we said, it changes your perception of things. So sometimes it can even alter the way you see things. Let's say, like, you have the way you perceive things. Let's say there is a train which is coming. Your mind because of the erroneous perception, might not hear the sound of the train. It might just see beautiful colors. So the train, the train is, it's a train. It's making, of course, the all the sounds it's supposed to make. But you, when you're on this drug, instead of seeing the train, you're seeing a beautiful colors approaching. So in that, because of that perception, you might decide, you might not be able to see the danger, and you will try to cross, you will try to continue moving on with your business, and for sure you're going to be crushed by the train. Of course, another perception is that when you take some of these drugs, they kind of again give you the perception, or they give you the feeling that you can be able to fly. So you find some of these people, you think they committed suicide, but it was not intentional. But in their thinking, because of this alteration of the mind, they think they can fly. So they go to a house, 4th floor, and they fly. They'll just crash and die. And people will think, of course, they have committed suicide. So that's what we are saying, that most of the people do not die because of the drug effect, but they die because of the effect of all of the way the drug affects, alters the mind. The way the drug alters the mind, their thinking, and so on. That is what normally causes their death. So we are saying people have died walking out onto a freeway or attempting to fly. So not the effects of the drugs, not the toxic effect of the drug, where we are talking about it can have we normally say it can have carcinogenic effect, it can have toxic effect. And so that's what we are saying. You're saying it is those mind distortion effects that can actually make the person have a changed behavior, and therefore in that causing death. Some of the phenylethylamine hallucinogens have caused the phenylethyl. So these ones, remember, so because we are going to look at this. So some of the phenylethylamine hallucinogens, however, have caused the overdoses, although a dose is greater in excess of active doses. So we are saying in the active doses, they are normally safe and do not have much problems. But of course, as we have said, they are mind expanders. We have said, if you look at this, we have said that they are the alter perception, the alter mood, they alter the cognitive process, and we have said they are mind manifesting expanders, they are mind disturbing, they produce dreams, they can bring about psychosis, and because of those changes, the drugs can end up causing the person, as we have said, to have altered behavior, and indeed, therefore, death. Classic hallucinogens do not create dependence or addiction. Addictive substances like cocaine, nicotine, caffeine affect the dopaminergic transmission and reward system in the brain. So they do not cause addiction. The classic hallucinogens lack affinity for dopamine receptors and dopamine transporters, and there is no evidence they produce addiction. So those are some of the common features of the 5-HT2A agonists. So now we start with the phenylethylamines, and of course we have said again. I want us to get this. The phenylethylamines are this one, phenylethylamines. So even when we look at the phenylethylamines, we are looking at them as 5-HT2A agonists. So we are starting with this class. The phenylethylamine class of hallucinogens can be further subdivided into one, the phenylethylamines, meaning these ones, the alpha carbon has not been substituted. And we have an example of mescaline, and we're going to look at its structure in a minute. Then we have the phenyl isopropyl amines. Phenyl isopropyl amines, and this is where we have the amphetamine derivatives, whereby you have alpha carbon, it increases it decreases the rate of metabolism of the amino group through oxidative deamination. So I hope but we will see that in these compounds, the structural modification is slightly different from the structural. Phenyl isopropyl or amphetamine derivatives, where you have number 1,2,5-dimethoxy, 4-methyl-amphetamine. So remember, when we were looking at the CNS stimulant, we said you cannot. When you substitute, even when we put a chloro group, dopaminergic activity, there was change in activity and there was a reduction in stimulant activity. So here we are saying you can see this compound 2,5-dimethoxy, 4-methyl, all these 2-methoxy groups and the methyl group are actually on the aromatic ring. And then dimethoxy methyl amphetamine, or DOM. And then you have the two, we are talking about the phenylethylamines. So the general structure, there's a specific one, is phenethylamines, because you can see this position there has not been substituted. And definitely this is an ethylamine. Of course, you do have your phenyl. And as we look, when you look at the structure of mescaline, you can see this is position number 1, position number 2, position number 3, position number 4, position number 5. And therefore, we can say mescaline is 3,4,5 trimethoxy phenylamine. So that is the structure. And you can see when we look at the other structures we were looking at, the difference is that, of course, that position is not substituted, because remember we did say the phenylethylamine structure does not have any CNS activity because of rapid metabolism. And that's why we introduced a methyl group there. So we do not have a methyl group there, but we have the 3-methoxy groups which are on the aromatic ring. Mescaline is a major psychoactive component of the peyote cactus. So it's naturally occurring. It is a very weak hallucinogen, very, very weak hallucinogen, but it does have hallucinogenic activity. Again, one has to be careful about the plants which are out there, because some of them can cause toxicity. And indeed, even animals, somehow they're able to differentiate. And if you find any plant that is not eaten by animals, you need to be warned that there could be problems. The basic structure of the phenylethylamine, hallucinogens and substituent positions. So this is now our structure here. That's our basic structure. So we are saying you can have a substituent at R5, R4, R3, R2, and of course you can have a substituent at position, the alpha position. And when R is a hydrogen, of course, we are talking about the phenylethylamines. When R is a methyl groups, then we are talking about the phenylpropylamine. And we had already mentioned a few examples. We are looking at mescaline as the example of the phenylethylamine, and we are looking at those compounds that we've already mentioned. And you can see they are here. So for mescaline, all the groups are methoxy, but for the phenyl propylamine, you can see we're having different groups. R is differing with increase, or is being modified with increase of activity. So if you look at the relative potency, you might not require the dosing, but you can look at the relative potency when R is a methoxy group. When this R is a methoxy group, that means you have mescaline, then we are considering that the relative potency is 1. When we increase the size of R to an ethoxy group, you can see relative potency is 7. So we are saying, therefore, of course, increasing the size, not to a specific size like ethyl, increasing the alkyl group from methyl to ethyl further increases the activity. And of course, that is because you are increasing the lipid solubility of that molecule, its ability to penetrate the BBB. When R is an S-methyl, again, the S also has increased lipid solubility. Again, when it's an S-ethyl, the same story is repeated. But I want to believe you cannot go beyond the ethyl group, that is CH2CH. Because again, when you make it very big, you have a problem. If you have too much lipid solubility, always remember you have depotization. And again, when you have very huge groups at one particular point, normally the molecule is too huge, the steric hydrons, there is interference with binding on the receptor. The accessibility of the receptor becomes a problem. So we are therefore saying that this group here, even for the phenyl, ethylamines can be structurally modified with increase of activity, where increase in an alkyl group increases lipid solubility. Of course, it is usually supposed to be a maximum beyond which you cannot increase the group any further, because of, we have seen depotization and steric hydrons, which will interfere with that molecule binding the receptor. So those are just then we have, I think it's the same compound, and we are looking at the relative dosages. And of course, the one which is relative potency one, we will have a higher dosage. And as you go down this way, you expect that there is an increase in potency and therefore a decrease in the dose that is going to be given. Then mescaline, its metabolism, and it can be metabolized through monoamine oxidases, mescaline monoamine oxidases. And if that happens, then this monoamine oxidases, remember, they will result in oxidative deamination, usually first to an aldehyde and then oxidation of the aldehyde to the carboxylic group. And if that happens, nothing else has changed. We still have the 3,4,5-trimethoxyphenyl acetic acid. It can also be oxidized, also to a lesser extent. This can also happen, dismethyl mescaline, and that dismethyl mescaline R, when R is a hydrogen. So that means for us to get dismethyl mescaline is where there is oxidative dealkylation of one of the methoxy group, oxidative demethylation of one of the methyl groups. And if that happens, then you will get dismethyl mescaline. It can also, because this being an amino group, amino groups can also be acetylated in a reaction catalyzed by N-transferases, N-methyl transferases. So that can be acetylated where you have N-methyl transferases, and that, of course, will also, remember, acetylation does not usually increase water solubility, but usually terminates the reactivity of that molecule. So that can also, that route of metabolism can also happen. Then let us look at the phenylpropylamines, or the amphetamine derivatives. The other one were phenylethylamines. So now we are looking at the amphetamine derivatives. The minute you put a methyl group there, the compound becomes amphetamine. And again, alpha methylation of phenylalkylamine increases CNS activity. The same reason we did give when we were looking at amphetamine, and this is not because of the binding or because of increased lipid solubility. Mainly is because that group that has come in at the alpha position increases the steric hydrons and reduces the rate of metabolism or the rate of oxidative deamination of the amino group. Increased activity may not be strictly through binding efficiency, but decreased metabolism due to steric hydrons, which we've already mentioned. Alpha substitution produces optical isomers with the levo R. So again, please note, when we were looking at amphetamine for stimulatory activity, we said it is a dextrose. So again, here we have an inversion of the stereochemistry. Hallucinogens, the enantiomer, which has more activity, is the levo R, whereas the stimulatory activity is found mainly in the dextro S isomer, meaning the receptors are different, has high activity than the S-dextro isomer. So that is quite important for us to note. And ortho, meta, or para substituted amphetamine has no hallucinogenic activity. So if we just put one substituent, whether at ortho, you put, or at para, or at meta, the resultant compound does not have any hallucinogenic activity. 2,5-dimethoxy and 2,4,5-trimethoxyamphetamine have higher hallucinogenic activity. So again, substitution, as we have already said, unlike in the CNS stimulants, substitution with methoxy group on the aromatic ring again increase a hallucinogenic activity. Di and triaromatic substitution increases potency, and we have already given quite a number of examples of that, the DOM, the DOI, and the DOB. The 2,5-dimethoxy 4-methylamphetamine is a psychedelic and a substituted, of course, amphetamine. Remember, psychedelics is just another name for hallucinogens. N-methylation, that mono decreases or abolishes. Again, another difference with the stimulants. Remember, we did mention if we do N-methylation of, when you look at the amphetamines, or you do N-methylation, that increased activity. But if you go beyond that, you do dimethylation, or you increase the size of the alkyl group, remember, we did mention that indeed abolishes or diminishes the stimulatory activity. So again, please do note the differences. So N-methylation or monomethylation decreases hallucinogenic activity. So this we've already mentioned. When we look at these drugs, again, you can also have introduction of rigid structures. So you can also have introduction whereby if you look at this, some of these compounds, like you had a methoxy group at this position as a substituent. Remember, you said position 1, 2, 3, 4, 5. There was a substituent at position 5. So if you look at this group here, if it was a methoxy group, it was OCH3. This was CH2. There. CH3 in the methoxy group. So all that has happened is that the methoxy groups now, the cyclization whereby the oxygen and the methyl group of the methoxy group at position number 5 now is has been derivatized into a cyclic ring, giving us, of course, this is the dihydrofuran ring. So giving us this cyclic ring with retention of activity. Indeed, when total aromaticity was attained, whereby if you look at this here, if you look at this is now the furan ring. And if you look at again on this position, remember all they have done, again, you had a methoxy group at position number 2. So the methoxy group also has been made into a cyclic ring. The methoxy group here again made into a cyclic ring. This compound, incidentally, and you can see you've retained your bromine, was found to be the most, to have very high hallucinogenic activity, almost equivalent to that which is found with LSD. So all we are saying is that the methoxy group, both the methoxy group at position number 2 and at position number 5 can be part of a cyclic ring, indeed part of a cyclic furan ring with retention of activity. So the fully aromatic compound is a fast alkylamine derivative to show higher potency. It's a fast alkylamine. In fact, it is a propyl. We have said propylamine derivative to show a higher potency than even LSD. So we only, that is still part of this. That's still part of the SAR, that indeed you can form rigid once this molecule, the phenyl ring, is held like this from the two sides. That is a very rigid molecule, and it's usually planar, but it is still able to bind the receptor. So I think now with that, we have looked at the phenyl alkylamines, where you have the phenyl ethylamines, and we have looked at mescaline and perhaps some of the derivatives, and also the phenyl propylamines, where we have looked at derivatives of amphetamine, both rigid and aliphatic, and we have discussed what can happen or what happens to the structure on structural modification of those groups. So I think we are done with that. We can now move to the next class, and the next class is the tryptamines. Next class is the tryptamines. I want us to be able to see that we are following our order. You can see ego lines. Yes, we have discussed the phenyl ethyl. In fact, we have discussed the phenyl alkylamines, because we have both the phenyl propyl and phenyl ethylamines, and of course also we have discussed. So now we are going to the next category, which is the tryptamines. And then finally we will look at the ego lines. So I just wanted to confirm that we are still following the order. The tryptamines, which are also the tryptamines, are idoacylamines. The tryptamines have structural similarity, now not to amphetamine, but or not even to dopamine, but now to serotonin. Serotonin is an indole derivative. So serotonin in itself has no psychoactive activity on oral administration due to rapid metabolism and high polarity. So you cannot give it orally, but you could give it in a way it gets into the brain. Of course, high levels of serotonin can bring us psychoactivity. What happens when you do N substitution? Wow, look at this. Of course, we did not have indole or tryptamine derivatives for for the for the stimulants. So what happens when you have N substitution? The N monomethyl of tryptamine gives a compound with no activity. So N methylation again does not give us any activity, just as we said N methylation, monomethylation of the phenylalkylamines. N dialkylation with appropriately large groups gives active compounds. So N dialkylation with appropriately large groups will give you, in other words, appropriately, you must substitute with the right size of the alkyl group. If you do too big, of course, again, you will not have activity. And dimethylation again gives compounds with no oral activity. So for you perhaps to get oral activity, then the groups must be slightly larger than the methyl group. So again, we are seeing a difference even with the alkylamines or the phenyl alkylamines, because we did mention, like when we were looking at the stimulants, again, we can see some difference. But of course, we are saying here, this structure is completely different. This is an indole, and the other one is an phenyl alkylamines. So we're saying N dimethyl. So again, could be issue of structure, could be issue of binding, the type of receptor that we have, because when we look at the other compound, one methylation gives us enough lipid solubility. So most probably it is an issue of the kind of receptor that we have. And dimethylation of tryptamine gives the compound bufotenine, which is a very weak hallucinogen. Remember, we did mention the N-dimethylation is not very effective. Methylation of the hydroxyl group of bufotenine to give 5-methoxy N-dimethyl tryptamine increases activity. Let us look at that. That is our structure. This is our tryptamine. Tryptamine is when you remove the hydroxyl group. Serotonin has the hydroxyl group, so that's the only difference. So that's why we call serotonin 5-hydroxy tryptamine. 5-hydroxy, because we are starting from here, position 1, position 2, 3, 4, 5. So the tryptamine is without the hydroxy group. So when we look at the bufotenine is when, first of all, you do methylation. You increase, or you have a slight positive influence on the hallucinogenic activity. But if you leave this group as a hydroxyl group, then you find that that compound also will not still have oral activity. But you can also block that group, and this is what we are calling dimethoxy. This is what we this is the one we gave the name methylation of the hydroxyl group of bufotenine, because bufotenine is just the end methylation of tryptamine. So you first of all get tryptamine, and you get bufotenine, and then you are saying you get hydroxybufotenine will be dimethylated compound with the hydroxyl group, and now you get 5-methoxy N-dimethyltryptamine. It will have increased. You're saying it will have increased activity. We are calling it N-dimethyltryptamine. We're using the word tryptamine here because we've already, this name is outside. So we cannot call it serotonin, because we're already calling it 5-methoxy. N-dimethyltryptamine increases activity. In other words, the hydroxyl group, of course, the hydroxyl group on the aromatic ring, or the phenyl ring, has much higher polarity. So again, when you methylate it, again, you're increasing the lipid solubility. It looks like the indole derivatives they do require molecules with quite a lot of high lipid solubility for them to be able to effectively interact with the receptor. Those are the structures we were looking at. That is tryptamine, that is serotonin, that is bufotenine. That is bufotenine. Now, if you methylate that group, then you get the methoxy. That is the methoxy, and then dimethyl tryptamine, because that compound now will be tryptamine. And that is a compound we are saying it has a slight increase in activity, and we can tell, we can't be able to say it is because of the fact that methylation of the free hydroxyl group will increase lipid solubility and allow that molecule to be able to penetrate the membranes much more readily to give us some activity. Then again, we are still on the tryptamine. In the absence of hamine containing plant, the tea has no unusual effects. Why? So we are only saying that if you look at DMT is a psychoactive ingredient. So in tea, that is, there is, I think, a particular tea which has that. So if you have the dimethyl tryptamine, we have said dimethyl tryptamine has minimal, in fact, has no raw activity. But if you give it in the mixture of hamine, this is the structure of hamine. If you give it in combination, hamine acts as a blocks as an antagonist of the metabolizing enzyme, the monoamine oxidase enzyme. And therefore, if you give dimethyltryptamine with hamine, you find that the effects of dimethyltryptamine will be felt. If you give it orally, you will feel the effects of dimethyltryptamine because the peripheral degradation of the dimethyltryptamine by the B monoamine oxidases will not occur, and therefore you will get the effects. That's just to say, that is just almost to prove why the dimethyltryptamine has no oral activity. It is because it is not able to get into the brain as that compound because of rapid metabolism. So the dimethyltryptamine is a psychoactive ingredient, but it's not orally bioavailable. It is rapidly degraded by monoamine oxidase enzyme. Hamine is a monoamine oxidase inhibitor, and so it makes the DMT orally bioavailable. So we are now, so those we have now looked at the we have looked at tryptamine. How can we structurally modify it? So we did mention, even in tryptamine, when you put the 5-hydroxy group as found in serotonin, it will decrease the activity. Methylate it, you slightly increase the activity. So that we have actually looked at that in detail. So let us look at also, we are still on tryptamines, and we do have some tryptamines that are naturally occurring in mushrooms. And I remember this, I think, is a question I had given you for your assignment. I haven't looked at it because I'm marking other for the lower classes. So if you look, there are some mushrooms which are very poisonous, and those mushrooms contain psilocybin. If you look at psilocybin, there is a slight change or difference between psilocybin and 5-hydroxytryptamine. Of course, you find that has been or if let us say let us not say with let's say with serotonin, because of the hydroxy group. So that, of course, has been dimethylated, and that we have said once you dimethylate, you slightly increase the activity. But if you look at this position, if you look at serotonin, the hydroxyl group is usually in position number 5, not in position number 4, as in psilocybin. So if you look at psilocybin, there is a slight difference. It's where it can write the presence. It refuses to write. I don't know. Anyway, I don't know. It has refused to go to number 5. So if you look at psilocybin and serotonin, you will see there is a slight difference. Or if you look at it and compare it with the hydroxyl bufotenide, you see there is a difference in that the hydroxyl group is at position number 4 rather than at position number 5. And I think I'd asked you what the influence of that, and you find that psilocybin mushrooms contain psilocybin, which is a tryptamine hallucinogen. So although you are going to take the mushrooms orally, and they do have an hydroxyl group within the phenyl ring, they will bring you toxicity. And the question is why? Why is it when you change? Because this is indeed a constitutional isomer. This is a constitutional isomer with when you have your hydroxyl group at that position. And why does that happen? And of course, why that happens is that when you do it this way, because this is hydrolyzed in the body by the phosphatases to give us the hydroxyl group. And now, when you put the hydroxyl group at position number 4, the hydroxyl group and the terminal amino group are in close proximity. They are closer to each other than when the hydroxyl group is in position number 5. And once you have this hydroxyl group and that dimethyl amino group, and of course the nitrogen is what is most important, when they are that close, they can form hydrogen bonds. So the close proximity of the hydroxyl group and the terminal nitrogen allows those groups to form hydrogen bonds. And once they form hydrogen bonds, what does that mean? It means that the basicity of the nitrogen is much reduced. Because remember, the hydrogen bonds is usually, in fact, formed between the hydrogen. There must be the hydrogen in between. So the hydrogen carrying a delta positive, the oxygen carrying a delta negative. So the hydrogen is interacting with the nitrogen, and the nitrogen is donating its lone pair of electrons. So by nitrogen donating its lone pair of electrons, it means it reduces its concentration of electrons or its basicity, and therefore the tendency of that molecule to undergo ionization decreases. And once the tendency to undergo ionization decreases, it means this drug, the psilocin, will have a lot of it. You can either call it psilocin there, so where you can put PSY, it's the same. So you will have, it's not here, you will have a high concentration of this drug in the anionized form in the body at physiological pH, because you have reduced the basicity of the nitrogen. If you have more of that molecule in the anionized form, then that molecule will have much higher lipid solubility. And because it will have much higher lipid solubility, then you will find that that drug will be able to penetrate. It will be able to penetrate the BBB and be able to give us quite good activity. So those are some of the examples that you can have constitutional isomers. One has activity, biological activity, the other one does not have. And the reasons can be, as we have explained, that one, like here we can talk about one, once you have the hydrogen bond, also the terminal nitrogen, it's like it is shielded. And if it is shielded, the accessibility of the monoamine oxidases is reduced. So we are talking about the molecule has lower basicity, lower ionization. We are also saying the terminal nitrogen, which is metabolized by monoamine oxidases, is also shielded. It's shielded, it's protected because of this other extra bond. Because whenever you have a bond, again, remember there are electron clouds. So that nitrogen has been protected from rapid metabolism. Of course, it will be metabolized, but at a much slower rate. We have also said because of the fact that the compound has lower ionization, its electrons are utilized, it has higher lipid solubility, therefore better penetration through the membrane. So you can see that here we don't usually have constitutional isomers, but this is an example, because we also mentioned constitutional isomers when we were mentioning the isoflurane. I think there was fluorine and isoflurane, and we did mention there was also constitutional isomers. But constitutional isomerism is not very common in drugs. It is not as common as the optical isomerism. So again, they are saying that the serotonin, 5-hydroxytryptamine, that is psilocybin. So you can see the difference, that this has been methylated. There's dimethylation, and of course, the hydroxyl group has shifted to position number 4, and of course, there is a phosphate molecule. And then, of course, we did mention B49, where you have the hydroxyl group, and again, so it is serotonin with demethylation. And then, of course, we did mention methoxy before 9, where that hydroxyl group can also be can also undergo methylation. So if you look at in the body, you can start with tryptophan. Remember, tryptophan is an amino acid, and you can see that, and you can undergo decarboxylation to get tryptamine, and then the tryptamine can undergo several stages to give us the hallucinogen. So, in other words, we are saying tryptophan can be the starting material in the synthesis of the hallucinogen or the hallucinogens. So biosynthesis of psilocybin. So as we have said again, you can start with L-tryptophan, aromatic amino acid decarboxylase, aromatic amino acid decarboxylase, and once that enzyme brings about the decarboxylation, those carboxyl group goes, and of course you get the tryptamine, and then you can now have the tryptamine methyltransferase, which transfers to methyl groups, and of course we get the dimethyltryptamine, and then we have 4-hydroxylase, which adds a hydroxyl group, and that gives us the psilocin, and then the phosphatase enzyme. The psilocybin kinase, the phosphatase hydrolyzes the psilocybin kinase, and the psilocybin kinase now will add a phosphate group on the 4-hydroxyl group to give us the psilocybin. So this is most probably what happens in the mushroom when you are synthesizing the psilocybin easily. It's an easy process, whereby, of course, also the precursor like L-tryptophan, I would expect, because it's an amino acid, it can't be readily available. So we are looking at psilocin versus Bu49, because they do share their structural, their constitutional isomers. That position there is the same. That position there is the same. It is only the hydroxyl group that occupies different positions. So we are asking ourselves, why then would psilocin have much higher hallucinogenic activity compared to Bu49? And of course, these two compounds are constitutional isomers. There's a critical difference in the activity. Psilocin is orally active. That's why I said even when you take the mushrooms orally, they will give you a hallucinogenic toxicity. And I have explained, you have the hydroxyl group, where this is a delta negative, that's a delta positive, and you have the nitrogen, which of course also, because of its lone, it has a lone pair of electrons. So you have this as a lone pair of electrons. Of course, the carbon will carry a slight delta positive because of the electronegativity. That's all these are showing. The nitrogen has high electronegativity. It will pull electrons towards itself so that it carries a large delta negative. And on top of that, let us be reminded, it also has a lone pair of electrons. So it will form a bond, usually a hydrogen bond with the hydrogen, because a hydrogen bond is where you have this either oxygen, nitrogen, oxygen, fluorine, of course, connected through a hydrogen. So it will form a hydrogen bond, and in forming that hydrogen bond, that is where we have said there will be several effects. So this is the same drug. So you can see this is the hydrogen interacting here. So we have what we're calling the closed loop. So this whole, it's a closed loop. And because of that closed loop, the nitrogen has lower basicity and is shielded. And also we have the closed loop. This closed loop, again, also prevents or protects the nitrogen from, that's the one we are calling the loop, or the closed loop shields the nitrogen such that its metabolism by the monoamine oxidases is reduced. The formation of the hydrogen bond, we have said, reduces the basicity of the nitrogen and therefore reduces its protonation. In reducing its protonation, it means you will have the anionized psilocin being in higher concentration, and the anionized one will have the higher lipid solubility. And I hope That is how you answered your question. I haven't as yet looked at it, but I will. So psilocin, the hydroxyl group of psilocin is a little bit closer to the amine. It is able to form a hydrogen bond between the 4-hydroxyl group and the 3-ethylamine group. This hydrogen bond shields the electron lone pair of the amino group from deamination by monoamine oxidases, which means that unlike bufotenine, psilocin is orally active. Number 2, the hydrogen bond also decreases the molecule's proton accepting capacity. That is, it reduces its basicity. It has a much lower pKa, decreasing its rate of ionization. Therefore, at blood pH, there is more of psilocin in the non-ionized lipid-soluble form, which is able to cross cell membranes and thus enter the central nervous system. This is the same thing I had explained. Also, psilocin, from what we have said, it has lesser protonation, is a more lipid compound closer to an ideal value for the drugs to effectively enter and bind to the appropriate receptors in the CNS. So this is the anionized psilocin. It will have much higher lipid solubility and it will be able to penetrate the CNS. So there is the reduced metabolism, there is the reduced ionization, and there is increased lipid solubility of this molecule. Then metabolism, of course, we said we will start with the psilocybin within the mushrooms, and there can be the alkaline phosphatase, and with the alkaline phosphatase, then you will remove the phosphate molecule, and that will directly give us the psilocin, and this is the one which is pharmacologically active. So this is a prodrug. This is the one which is pharmacologically active, and it can undergo, of course, with that hydroxyl group there, it can undergo glucuronic conjugation to give us the glucuronide, which is highly water soluble, readily moved from the body. All it can undergo monoamine oxidation. Of course, it will undergo, but at a slower rate than bufotenine. So it will go metabolism at a much slower rate. And when it goes metabolism at a much slower rate, it will give us time for quite a lot of it to have penetrated the BBB and to bring the central effect. So therefore, it is shielded, but it will still undergo oxidative deamination to give us the acetaldehyde, 4-hydroxyindole 3-acetaldehyde, that's the acetaldehyde. And now the acetaldehyde can either undergo oxidation or it can undergo reduction, usually either oxidation or reduction. If it undergoes through oxidation, it will give us the alcohol. If it undergoes reduction, it will give us the if it undergoes oxidation, it will give us the carboxylic group. If it undergoes reduction, it will give us the alcohol. Reduction gives us the alcohol, and when of course, will be CH2OH, that is the alcohol, and that's a reduction to give us the 4-hydroxy tryptophan. When it is oxidized, it will give us the acetic acid derivative. So the name could come. The correct name. Is hydroxy indole. In case we are saying, in case now this R here is a COH. So that is a COH. Of course, as I've always said, carboxylic acids always take priority. So the compound will be an acetic acid. So it is hydroxy indole 3-acetic acid. Hydroxy indole 3-acetic acid. So that will be the product when an oxidation occurs, when a reduction occurs, it will be an alcohol, and that's what we are calling 4-hydroxy tryptophan, 4-hydroxy tryptophan, and when it is an oxidation, hydroxy indole 3-acetic acid. And it's 3-acetic acid position 1, 2, 3, 3 from there, 3, and definitely that is acetic acid. So hydroxydo 3 acetic acid. Structure activity relationship. Again, when we look at these compounds, the indo derivatives, unlike, again, there is quite some difference on the aromatic ring. Remember when we were looking at the alkylamines, the propylamines, we were able to observe that you could do up to 3 substituents, or you could have up to 3. You could have a substituent at position 1, that's position 1, 2, 3, 4, up to 5. But we are saying for the tryptamines, you're only allowed 1 substitution. More than 1 substitution will have an influence, negative influence on the reactivity of this molecule. So we can be able to compare different compounds. We can be able to compare the N-alkyl substitution of the phenyl alkylamines and of the indo alkylamines. We can be able to do that. We can also be able to compare the aromatic or the indo ring, because this also causes the whole indo ring substitution. And what we are saying is that for the indo derivatives, we are not allowed to have a lot of substitution on the phenyl ring of the indo heterocyclic ring. We are not allowed to do a lot of substitution. Only one methoxy group is responsible for maximum activity. Again, remember, we're just as we said with the alkylamines, like the phenyl alkylamines, these groups can actually be slightly larger. They can be slightly larger than the methyl group. For you to get hallucinogenic activity, these groups require to be slightly larger. And we did say that even for the phenalkyl and for the phen-propyl amine derivatives. So when we look at R1, R2, like if it's hydrogen and hydrogen, we will have position 1. So we always start there, 1, 2, 3, 4, 5. So you can see, of course, also for maximum activity, because these drugs are binding the receptor that is bound by serotonin, definitely agonists. So you can see that group there is at the same position. So the position there is also retained at position number 5. So if you look at this compound, therefore you have hydrogen, and you have a 5-methoxytryptamine. It is not a psychedelic, so there is no dose. When you have hydrogen methyl, again, remember you put a hydrogen methyl, again, it does not have any psychedelic activity. We are saying, because we remember we did mention monomethylation does not give us activity. Dimethylation at this particular position with groups that have an appropriate size, like ethyl propyl groups, the small groups like methyl, give us almost negligible activity. So you do have, of course, both methyl groups there, 5-methyl DMT, so 5-methoxy dimethyl tryptamine, and it does have some positive psychedelic activity. We can use 6 to 20 milligrams. So at least dimethylation, as we saw with bufotenine, and even with psilocybin and psilocin, dimethylation can give us activity. But you can see that this group here has been also unmethylated. So therefore, if the methylation there and the methylation there is important for that compound to have any oral activity. Again, you can have a propyl group. Remember, we did say you can increase the size, propyl group, and of course, again, methoxy group. And again, this was positive LSD, like psychedelic activity. I did not go beyond that, because beyond that, the groups are too large, and some of the activities are not yet even established. So the tryptamines are extremely sensitive to substitution on the EDOM ring, and nearly any substitution besides those shown previously, where we showed only methoxy, results in diminished activity. So for the tryptamines, the only substitution that is allowed is the 5-methoxy group with retention of activity. The indoor ring has also been replaced. There has been structural modification in the indoor ring, but no other ring has been as good or has produced optimal activity as compared to the indoor ring. So switching the indoor for another heterocyclic such as benzofuran or benzothiophene produces compounds with modest but diminished activity. And that is why the compounds that are responsible for maximum activity are those that have the indoor ring are methylated, all of dialkylated and dialkylated, and of course methylated at the 5-hydroxy group. Look again, we had said this group also can be substituted. If that is substituted, of course, it will give us the propyl derivatives, not ethyl, but now, of course, there will be propyl derivatives. And if that happens, as you can see here, we've already mentioned that, of course, that will introduce a chiral center. And again, the stereochemical requirements for activity is what we have said. The R levo has much more activity than the S dextro, which again is very different. It is very different from what we observed with the CNS stimulants, where we talked about amphetamine and methamphetamine derivatives. So I think that now finishes the indoor derivatives, and we go to the last one, which in that category is LSD. And LSD, again, if we look at it carefully, we will be able to see it is almost, you can see it's almost there. It is, of course, it has that indo. There's an indo derivative, and you can see there because it's not a tryptamine. That's why we are putting it differently. But you can see this that we have the characteristic structure there, which we have in the tryptamines, whereby this is the indo ring, and then 1 carbon, 2 carbons, nitrogen here. And if you look at your nitrogen, as we have just discussed, it has that substituent and it has that substituent. Again, therefore, when we look at LSD, we are able to see that it has that basic requirement. It has that basic requirement where we can see it as even, we can even call it a phenyl. It still has a phenyl ethylamine. But of course, this one we are looking at it's an indo ethylamine substituted with the nitrogen disubstituted. And that, of course, we know is what is required for maximum, that is required for good hallucinogenic activity. So we are, again, if you look at it, there is also this group here, which has been found to be very important. When we call it LSD, we are calling it lysergic acid diethyl amide. So you look at this this is a 1-ethyl group there. That's the other group right there, and you can see the amide. That's why we call it lysergic acid diethyl amide. So that is the full name of LSD. So we are saying, when we look at the SAR, we are saying that the substitution on this amide, on this terminal nitrogen, again must be preserved. You can't just substitute within a group. If you do so, then there will be drastic loss or drastic decrease in activity. Any change in the amide substitution results in substantial decrease in potency. The LSD's extreme in vitro potency does not correlate well with its 5-HT or 5-hydroxytryptamine 2A binding, indicating it most probably has an additional mode of action. So we are only saying it is a very, very strong hallucinogen, very highly potent as hallucinogen, and we are only saying it's binding with the receptor, or its high activity cannot be well explained by the way it binds with the 5-HT2A receptors. There might be another mechanism perhaps which has not yet been established. But we are saying nevertheless, it is a 5-HT2A agonist. And of course, it can be able to do that because it has structural resemblance to both the phenylalkylamines or the indoalkylamines. It does have structural resemblance, allowing it to interact with the same receptor that those other drugs interact with one. Increase size. Preparation and stereochemistry, we've already mentioned. We haven't mentioned the stereochemistry. LSD is prepared by reacting lysergic acid with diethylamide. It has the chemical composition, that's its name. It has 4 chiral centers. And the reason why it will have 4 chiros, it has 4 chiral isomers, not centers. It has 4 different isomers, not chiral centers. Therefore, it has 2 chiral centers, and you can see one of the chiral centers should be at position number 8. So we have this as hydrogen. That's not a chiral center. So it has that chiral center at position number 8, and it has another chiral center at position number 5. So it has 2 chiral centers. When a compound has 2 chiral centers, that implies it can have 4 isomers. But it's only 1 isomer again. Stereochemistry seems to be very important in drugs. Mainly 1 isomer is the one which is psychoactive. And it is only the 5R, 8R dextroisomer which is psychoactive. A racemic mixture of LSD shows only have the potency of the dextro form. So we are saying it is the 5R, 8R isomer which is active, and it is the dextroisomer which gives us that. And of course, we can establish, so we have these 4 isomers. So you can have, of course, the LSD is this, where you have the 5R, 8R. And that is the LSD with maximum activity. When it is in basic media, it can undergo epimerization. We've discussed epimerization before in basic media, where the orientation of the amide, the orientation of the diethyl amide changes, and when that changes, that acquires an alpha orientation, and that is what we call the iso-LSD. And we have, of course, said these ones do not have activity. Then you can also have, again, the other isomer. You look at this isomer, it's a bit different from this one because it is the opposite. So in this one, you can see the position 8 is the one which has changed. It has the alpha orientation from beta. When you look at the LSD, position 8 has the beta, whereas position has the R. So this is the RS. This is the R, as we have already discussed. This is the S, R, and this is the R. This is the SS. So those are the 4 isomers you expect. So if you look at the LSD, which is also inactive, then there's a shift of the stereochemistry and the specific carbon atoms, where now 8 has the R and it is the 5 which has the S. And of course, again, in basic media, there will be, like, remember when we were looking at the tetracyclines, position number 4, we did mention you can have a shift, an alpha or beta. And of course, that when you change to beta, loss of activity. The same thing is happening here. So you can also have the LSD can have a shift or isomerism, or a shift of orientation at position number 8 to give us the SS isomer, which also does not have any activity. And I think that finishes the first group. I'm not moving very fast. The time now. Slide is this, slide number 31. Time, because we said we are having a cut. We have done 31 slides. I think, is that okay? So what I release usually. Is that okay? We have done 31 slides, which is enough for a lesson. so that I can release you and go and read, because preparing for a cut. It's already 10:30, almost 11. And then we will, one more lesson, I think, will be done. One more lesson, I believe, will be done, because we are only finishing. We are only finishing now those other categories, and they are not also very broad. So I think we can close there. 10:53. God being on our side, we meet next week. The cut is on what day? On Friday. When is the cut? Please, just one more lesson, just to tie things up, perhaps to wrap up things. But I think we're doing well. Two more lessons, we should be done. So I wish you well in your cut. Sign in students. I can see